Welcome, everybody, to Today in Space. We're back for another episode of People of Science. This week, we're very excited to have on Ethan Siegel, the author of Infinite Cosmos, a new book out on James Webb Space Telescope. Science writer, astrophysicist. Ethan, welcome to the podcast.
Thank you so much for having me. It's a real pleasure to be here, and I'm so happy to share a little bit of what we've learned about the universe with all of your listeners out there.
Absolutely. James Webb, to say that it's changed everything that we've even thought about the universe, it feels like an understatement because it's only just begun. But it's been a journey and a saga getting there, and I'm sure we'll dive into that. But what I'd like to do to start is tell me a little bit about your STEM origin story. What got you down the path of being a science writer and an astrophysicist, and then, eventually to this point with JWST?
I mean, you like for there to be like some nice, clean, like, oh, I've always did this, or it was Star Trek that triggered me to go into it. And my story doesn't have like one defining moment. It was
Hmm.
something where, there were a gradual series of like, I guess, critical moments in my life where I was really, drawn deeper into something that I had always been interested in. I was always a curious kid. I wanted to know how things worked. I had a microscope as a kid, I had a telescope as a kid. Both of them were not very good for doing the things I wanted to do. I
Yeah,
remember
yeah.
fiddling with my little microscope mirror, trying to reflect the light up onto the slide so I could actually see like the drops of blood when my dad would cut himself shaving. I remember not knowing anything about how to use a telescope. So I remember taking it out when the moon was full and pointing it right at the full moon and just being blinded by this white, you know, mass of filling the whole field of
I did the
view.
same thing. Yeah.
Um, it's
Yeah.
common mistakes you make as a kid. I was fascinated by other planets. I wondered where the earth came from. um, One big moment came for me. I grew up in a big city, and
Mm.
so a big moment came for me one summer. I was maybe 10 years old, and I was up in the mountains. I was out of the city, and it was dark. To me, it was like pristine dark skies. Now I know, like, okay, there were you can see the Milky Way if the skies are really pristine. But I must have seen hundreds of stars in the sky that night, and that was amazing to me.
Mm.
And I remember laying down on the hill in the grass, and all of a sudden having a feeling like I was super disoriented, like like this great black expanse was above me glittering with stars, and I had this disoriented feeling like if I wasn't careful I was going to fall up, like I
Yeah.
was going to fall up into the sky. And I remember uh pulling the blades of grass between my fingers and digging into them so that I wouldn't fall up. And of course, I did not fall up, in fact. So that was good. And in high school, I was interested in science and I studied a bunch of different sciences. And when I was in college, I was fortunate enough to go to Northwestern, and I got into a program called the Integrated Science Program. And I studied a bunch of different sciences, but I still didn't know what I wanted to do with my life. And when I graduated college, I went and I taught public high school after that. And it was
Mm.
while I was doing that that I said, okay, like this is fine, but it isn't what I want to do
Mm.
forever. So what do I want to do next? And although I didn't have the words for it at the time, I would describe what I did next as I had a crisis. And
Mm.
we typically talk about a crisis like, oh God, it's a state of emergency and everything is falling apart. And that's not what a crisis is. A crisis is when you come to a moment in your life where you say, look, I know that the path I'm going down is not the right path for me to continue down forever. So I need to do something different. And what is that different thing going to be? And I think confronting that not just then, but at various points through my life, has been a really valuable thing. Don't shy away from having a crisis. And for me, I said, well, look, I'm teaching now. If I could learn anything, what would I like to learn? And I
Mm,
was like, think big. Like, I want to know what the universe is, where it came from, how it got to be the way it is today, and what its ultimate fate in the future is going to be. And I looked into it and I was like, this is not a question for philosophy or religion or, some sort of, just I'm thinking and imagining what it is. Like, this is science. This is specifically a sub branch of astrophysics known as cosmology. And
mm,
if I was interested in the theories of this, theoretical cosmology is a totally legitimate thing I can study and go to grad school. And I was like, let me do some research and find where are the places that I can research this. I applied to 7 schools. I got into 5. I visited them. I chose University of Florida because they had an advisor that, I thought this could be a really good fit for me, and I wound up
mm,
working for him. His name was Jim Fry, and
mm.
I got my PhD with him. And then I went and I taught at University of Wisconsin for a year. I did a postdoc at University of Arizona. And same thing, while I was doing my postdoctoral research, I had another crisis. I was like, oh, I've been doing this research and I thought this was going to be my path and I was going to love it forever and ever and ever. And then I realized when I was doing that, I don't have the same working relationship with my postdoctoral advisor that I had with my graduate advisor.
Mm.
And I'm not as excited about the research if I don't have collaborators that I'm interested in working with. And so, have another crisis. All right. Well, you've learned all this, you have these skills, you have this knowledge. What do you want to do with it? And I said, well, I've always loved teaching. I've always loved sharing what I know with the world. And maybe science communication is something I can get into. So even though I went on to become a professor at University of Portland and at Lewis and Clark College in Portland, Oregon, I
Mm.
also started science writing. I started my own blog, which became Starts with a Bang. I started giving public talks and lectures, and I still do that. And I started writing longer form things, magazine articles, books. And here I am in 2024. And, this is 18 years after my PhD. Wow. And
Yeah.
16 years after I had that crisis as a postdoc.
Wow.
And this is me as a middle-aged man, and this is what I've been doing with my life since that time.
That's incredible, man. I love, to me, it sounds like one of the key things for you has been curiosity. It seems to be, you kind of chase the thing that then gives you that purpose, in whatever it is in science that you decide to pick up on. Does that sound
Well, one of the
accurate?
wonderful things about being curious is every time you're like, I have a question, and you have the question and you investigate the question and you've got a set of possible answers, and then observations come in and you get like an answer that rises above the rest, something that's like consistent and compelling.
Mm,
It always raises new questions, right?
mm.
So as long as you remain curious, you're never going to run out of things to be curious about, because as you learn new things,
Mm.
um, you discover that you didn't even know to ask these
Yeah.
questions, that now
Yes.
that you've discovered this new thing, you know to ask. And I feel like that is one of the lessons that has come up over and over and over again in just the 2 years that we've had James Webb Space Telescope science observations.
Yeah, absolutely. The crisis thing, I want to jump back to that real quick. We are no
Sure.
strangers to that. I think my whole journey with this podcast started after quitting a pack a day cigarette habit and, you know, going into the workforce, not finishing my degree, and this kind of, as you call it, crisis point happened, and it was like, what am I doing? And luckily, that challenge brought the change forward for me. And I got down this path of doing this podcast and got involved with NASA socials and stuff like that to this point where now you get to speak with people like yourself and share your story. So I'm I'm honored that you're here. Um, for the crisis aspect, is there a was there a problem that you faced? Like, could you give me like a quick example of those two crisis points? Like just a quick description, even if it's very general, because I think that's such a real thing that a lot of folks who work in STEM will face at some point. You know, your first job is not going to necessarily be your last job. Well, it's almost never that case. So,
No, and this is not like the 1960s
yes.
anymore, where you're not gonna get a job right after you graduate, and that's gonna be your career, and they're gonna give you a gold watch on your 25th anniversary, and then you're gonna retire and get a pension for the rest of your life. That is not the way the world works
Yeah.
anymore, and it hasn't been the way the world has worked for a very long time.
Hmm.
But for me, when I was actively teaching high school. I was
Mm.
22 years old, living in Los Angeles, California, teaching public high school. Um, you know, it didn't take me long to realize that this job was really hard on me,
Mm.
and I needed to start thinking about what it was I wanted to be doing long term. High school kids think they're clever, and with about a month left in the year, they'll start counting down the days until the school year ends.
Hmm.
And they don't realize that there are teachers who started counting in October. There were teachers who started throwing celebrations when the number of school days left went from 3 digits to 2 digits. And when you're doing things like that at your job, it makes you think like, hey, seriously, is this something I want to do next year and the year after that and the year after that and the year after that? This is my one life. I get
Yeah.
one life, and I'm the only one who gets to choose at the end of the day how I spend it. How do I spend my time? What do I invest in? And when I was having that crisis, what do I invest in? I remembered a situation that I was in a few months before
Mm.
where I was like, okay, I'm graduating college. I'm not sure what I want to do next. Nothing is set up for me, right?
Mm.
There's no go out and do this. And I was like, well, I'm going to move out to this place, and I'll find a place to live when I'm there. And when I got out there, the first thing I did was crash my car.
Oh,
And I was like, oh boy, like this is rough. I've got a little bit of money. I had like $3,000. I have a little bit of
yeah.
money. I have like no job. I have no car. I have no place to live.
Yeah.
Um, what am I gonna do? And then it occurred to me, right? I had like this epiphany that, like, hang on, I don't have nothing. I have this. I have what's up here. I
Mm.
have what I know. I have what I can do. I have what I'm capable of. And no one can take that from me. Crashing my car doesn't take that from me. Not having a job doesn't take that from me. Not having money doesn't take that from me. I I know inside, like, you have that, I don't know what to call it. You have that internal reserve of
Mm.
strength that when all the other lights go out outside, you give strength to yourself.
Mm.
And I thought, like, wow, I have that in me. I'm going to be okay. I'm going to figure it out. And I went to a high school that was by where I was staying, and I rang up the principal and said, hey, here's who I am. Here's my deal. I would like to teach physics. He had me come in. I showed him a VHS videotape of me teaching in front of a class, and
Nice.
I answered questions with him, and he was very impressed with me. I took that and I went to a different high school, and I said, hey, I can be at this high school or I can come to your high school. And I wound up getting a job for myself. That started that school year. I had a job to go to. And then when I discovered that wasn't what I wanted to be doing, right? Well, you can figure that out too. You can
Mm.
figure out what your next steps are going to be. I'd already taken the GREs, so I knew that I had
Good.
that in line. I asked professors for recommendations. And I actually, now that I'm talking about this, I remember one of the professors who I was expecting a good recommendation for. wrote me back something that was severely demoralizing,
Oh,
and told me that he didn't think I was good enough for this, and he would not
mm,
write me a recommendation. And he reached out to someone else who I wouldn't have even asked for a recommendation and said, and this person won't write you one either. And I was like, all right, well, I'm a little shaken, but I have other people who I know believe in me. And so I wrote to one of them and I said, hey, I want to do this. Here's some feedback I got. What do you think? And he wrote me back and he was like, don't listen to that guy. You
yeah.
can go to a graduate school. You can go to a good graduate school. Here's what
Mm,
I'd recommend for you. And so, you are going to have negative voices externally as well as internally, but you're also going to have people who believe in you. You're going to have people who will come to your aid, who will give you support, both in terms of letters of support or whatever, but also moral support in,
mm,
in terms of boosting you up and helping you believe in yourself when you have those self-doubts. Because if you decide I want to be an astrophysicist or anything, um, that's up to you. At the end of the day, you're going to go to the place and you're either going to learn how to do what you need to do, or you're not going to be able to do it. And whether you put in the work to get there, it's almost entirely up to you. There's some outside circumstances that people face, but it's almost entirely up to you. And so at that specific time in my life, I had a lot of people who helped me out. Roger Dixon, who's retired from Fermilab now, was very encouraging to me. Bill Halperin, who was a
mm,
professor at Northwestern in condensed matter, was very helpful to me, and it meant a lot to have support of people. And the same thing when I was having crises after I graduated, and I was like, oh, I thought this was what I wanted to do. I thought I wanted to do research. I had people both in academia and people who were in the world of science outreach who expressed that they believed in me, and also people who didn't express that they believed in me, or people who actively expressed that they didn't believe in me.
mm,
You have to I had a therapist once tell me with advice, any advice I ever got, that I should chew on the meat and throw away the bones. And sometimes you have to recognize that when you're talking to someone, what they're giving you is all bones and you should throw it all away.
mm,
Because at the end of the day, you have yourself to rely on. That's your number one thing you can rely on is
yeah.
yourself. And if if that foundation gets shaken and you don't believe in yourself, you have to lean on people around you who will help you believe in yourself again.
Yeah. That's powerful, man. We're talking mindset, we're talking, determination, and you get me all fired up over here.
Well,
Um,
at the end of the day, it's important to remember, like, I could talk your ear off about what we've learned and how we've learned it and all these exciting discoveries, but it's important to remember that you, me, everyone who's speaking here and everyone who's listening here, we're all just people. We're
yeah,
all just people. We've had lives, we've had setbacks, we've had good things, we've had bad things. And I think it's really important to remember that these things that are specific examples from my life are just my examples
right.
of challenges that we all face at some point in our lives.
Yeah, absolutely. Thank you so much. I mean, that's what this segment was meant to be, was to talk about the human side of science, So really, really appreciate you diving into that. And it feels like a perfect segue, just to talk a little bit about some of the research that you worked on. If you could just give us a brief little picture of what you were working on, what theories they were, and what you liked about them, and what was challenging about them.
For me, my biggest ideas were always about what happened in the early universe, right?
Mm,
Back when things were very different from how they are now, when we didn't have stars and galaxies in a cold, mostly empty universe that had clumped together.
mm,
What were things like way early on when things were hotter,
mm,
denser, more uniform? when instead of neutral atoms, you had an ionized plasma, where instead of just protons, neutrons, and electrons, you had high energy particles that get created in matter antimatter reactions. Maybe even really early on, back when cosmic inflation was ending and the hot Big Bang was just beginning.
Mm,
The stuff that I worked on was always, let's take some initial set of information, some set of initial conditions, and since we think we know the laws of physics and the contents of the universe, let's take them and evolve them forward in time and see if maybe some of what looks like it's a mystery today can maybe have some explanation in just this conventional physics we know.
mm,
So, I mean, I think the first idea I had was, we talk about the expanding universe in cosmology, and we say, like, okay, like I'm going to have these little, this mostly uniform universe that expands, but it's also full of matter and energy, matter and
mm,
radiation. And in some places, I'm going to have a little bit of a overdense region compared to the average. And in some places, I'm going to have a little bit of an underdense region compared to the average. And typically, what we say is, okay, well, in the overdense region, I have a little more gravity than normal. So it's going to preferentially attract the matter from the regions around it. Maybe this thing will grow into stars, clusters of stars, proto galaxies, something
mm,
even bigger, maybe. And over here in my underdense region, in the other way, where I have less matter than average, it's going to give up its matter to the denser surroundings. And maybe that will grow into a sparse region, a cosmic void where there aren't stars or galaxies, or at least where there are fewer of them than there are on average.
mm,
And that's part of the standard story. And for some reason, probably because I was taking graduate electromagnetism at the time,
mm,
I thought, hey, hang on a sec. If I have an overdense region and it's growing, but I also still have radiation in my universe, right? Photons and other things that exert pressure. Photons interact differently with low mass electrons than they do with high mass protons and atomic nuclei. So
mm,
I had this idea that, like, hey, when matter starts to collapse, what's going to happen is you're going to have slightly different forces acting on the negatively charged stuff, the electrons,
mm,
versus the positively charged stuff, the protons and the atomic nuclei. And if I'm having slightly different forces there, then maybe I'll get a charge separation and I'll get a
mm,
slightly different density of negative charges to positive charges in this region of space. And if galaxies, or the things that become galaxies, have angular momentum and rotate, then if I have a charge distribution that's non-uniform and motion within it, that's going to generate magnetic fields. And we see magnetic fields on the scales of galaxies. Where do they come from? Maybe they come from the early universe. Guess what? That could become a PhD dissertation. It could become my PhD dissertation. And that was my first idea. I think
wow,
it turned into my fourth paper,
mm,
because it took a lot of time to do the work for it.
sure.
But that was kind of how I got started, thinking about cosmology and the greater universe. was
Mm,
was having that idea and talking with my advisor about it, and gradually working out a simplified version of the problem for my qualifying exams, and then working out the fuller problem and how it pertains to the entire universe for my dissertation.
right.
And then shortly after I graduated, I had what is my favorite idea to say, like, okay, well, we have dark matter all throughout the universe and throughout every galaxy, and it shouldn't just be some uniform distribution of dark matter. There should be these subclumps of dark matter
Mm,
within it. That's something that is generically predicted by dark matter theories. And I thought to myself, well, hang on, we've got pulsars, these real accurate natural clocks in space, and we know how to detect clouds of matter that pass through pulsars because they will affect different wavelengths of light differently. If you have matter that intervenes, it's going to be made of grains of a specific size. And something that has a specific size is going to block what we say red light or long wavelength light and blue light or short wavelength light. It's going to block them differently. So if
Mm,
you see light from a pulsar where the redder wavelengths versus the bluer wavelengths are changing differently, that tells you something about the matter that's intervening. But if you have dark matter that doesn't interact with matter or radiation except gravitationally, then you should just see a gravitational time delay appear when a dark matter clump crosses your line of sight and then disappear when it finishes transiting your line of sight. And I worked out how long should it take for that type of transit to occur. And the answer was about 20, 30 years. And now pulsar timing arrays, specifically with like the nanograv collaboration, IPTA, the International Pulsar Timing Array, the IPTA, the European Pulsar Timing Array, China has one, right? You combine all of these together,
mm,
and now you're finally at the point where, hey, Ethan, if you stuck with that research, now's where it's really getting interesting. Now we can actually start looking at all these pulsars, and
mm,
people are learning about the gravitational wave background of the universe. People are soon looking forward to finding supermassive black hole binary systems that are
mm,
inspiraling and maybe even merging. But you could also potentially find, oh, if we have a big clump of dark matter moving across the sky and it's affecting some pulsars more than others, this might be something we can detect as well. And
mm.
so I think when you're trying to solve the mysteries of the universe, you need to look for whatever observable signal nature gives you and how could I leverage what nature might be doing to reveal something about something fundamental that might teach us something profound about reality.
God, I
So
love that.
those were my big topics of research.
That is very cool.
It's probably cooler when I describe it.
Well, it's such a unique life professionally, I feel like, to be in this big think of, trying to rue down the universe into as simple a way as we can try to calculate it and then test it. I mean, that's such a what does your day to day look like? Is it similar to Big Bang Theory, like Sheldon and those guys, or what?
Well, thankfully that's fiction, and
Yes.
it's Chuck Lorre fiction at that. So I those of you who have video on this can see me rolling my eyes involuntarily at that. But it's I would say when things are going well,
Mm,
you have interested smart people who are interested in similar things to you, and you're talking to each other about your ideas and you're working things out and you're
mm,
trying different techniques together, and you're collaborating in a fruitful way where you're very excited about what you're collectively working on. And I would say that is what the best part of my research career looked like.
yeah.
And when it doesn't go well, you have people who aren't interested in the same things as you, and you might be the only person interested in certain aspects of theory. And you might be surrounded by observers and instrumentalist who are great at what they do, but it's not what you do.
Right.
And I think in hindsight, one of the things I wish I knew more strongly to look for was who is a good intellectual fit for you
Ah,
to work with.
yeah.
Because who looks good on paper is not necessarily who's going to be good in person.
Mm,
And oddly enough, I remember thinking about that very hard when I was applying to graduate school, and then not so much when I was choosing a postdoc. Because when I was applying to graduate school, um, before I visited anywhere, my first choice was to go to University of Hawaii, and I was pretty sure I was going to work with a cosmologist named Nick Kaiser. Nick Kaiser was a pioneer in the field of gravitational lensing, which is
Mm,
how background light is bent by the gravity of a source that intervenes in between you and the background object. So if something intervenes in the line of sight, that gravity of that object will act like a lens, and it will bend, distort, and magnify the background objects.
mm,
Nick Kaiser was a pioneer in that. And when I met him, because I visited and I met him, and I was like, here's what I like, here's what I want to do, here's what I want to know. And he said to me, to his credit, he was just very straightforward. And he said to me, I'm going to stop you right there. That is stuff I used to do. I'm not doing it anymore. I'm transitioning into, and he told me the observational stuff he was interested
mm,
in. And he was like, are you interested in that? And I said, no, not really. And he was like, okay. And after visiting with the other professors there, I actually had a conversation with Esther, who
mm.
I learned went to the same high school I did,
Oh, wow.
uh, except a couple decades prior, which was an odd connection. And I talked with her about what I was interested in, what I wanted to do. And she said to me, you may want to think really hard about whether we are the right fit for you based on what your research interests are. Because, when you think about going to graduate school, in hindsight now, I tell people there are always three things to think about. One is, what is the overall strength of the department that you're looking at? Because you are going to be educated by this whole department, and you need to have a good feeling about, like, yes, this is a healthy environment that's going to teach me and enable me to learn all the disparate things I need to learn to grow my brain and get good
Mm,
at the thing I want to get good at. Number two is, you need to have a good advisor, someone that you work well with, that you enjoy working with, that you can have a fruitful working relationship with, and that you feel good about. You don't want to go
right.
home and be like, I hate every day of what I do, and I hate the people I work with every day for years and years and years. Realistically, you're looking at 5 to 7 years to get your PhD in America in physics, if that's what you want to do. And the third thing is, pick a place you won't be sad that you live. If
Mm,
you like the department and you like your advisor, but you hate where you're living, I give you about 3 years. And
yeah.
about 3 years into it, you're going to lose your mind, not in the fun way,
Yeah.
because you can't do it. You can't prosper living in a place where you hate living.
Right.
So those are three things: the overall strength of the department, your potential advisor, and can I live here, that you should absolutely look at when you choose a graduate school. I
Mm,
wish that I had done that for choosing a postdoc as well. I relied on some factors that maybe were not the most important to me, and I had other choices available to me. But I'm not sad with where I wound up with in my life, and I'm not sad that I wound up taking the path I did after having the crises that I had.
yeah.
Um, you know, could I have had a more successful research career where maybe I would have been the one to solve the mysteries of dark matter or dark energy, or why there's more matter than antimatter in the universe, or maybe I would have made some profound advance about cosmic inflation. It could have been, maybe that would have been me, but instead I'm communicating science to the world to the best of my ability. And one of the fun things that I can look back now at my younger self at and say is, hey, today Ethan Siegel has a job doing something that did not exist as a
Yeah.
career path while he was in graduate school. And that's an important lesson I feel for young people or even middle-aged people out there is the job you might have 10, 20 years from now, it may not exist today, but the skills that you're developing today and the talents that you have that you're cultivating
Mm,
today, those are still going to be a part of you down
yeah,
the road. So don't skimp on those. When you grow yourself, when you grow your mind and you grow your capabilities, that is equipping you for, with a unique set of tools that
mm,
you will be able to use whatever problems you're going to encounter to solve down the road.
100%. And thank you so much for sharing that and forgiving my if you will ignorance on the life of an astrophysicist. For me, I'm involved in engineering and in the tech world. So, I think my situation is a little bit more different, and I know there's a lot of listeners who are in the academic sense, and so I don't usually have great advice in that area, and that really blew me away, and it really transfers too to engineering and other disciplines. I mean, STEM is a gauntlet in life and just being a human being, and what it sounded like you're talking about is putting yourself in a scenario where your mind can flourish and then be at its best. And, I know I've taken jobs out of necessity because of location or, qualifications. I mean, my struggle for a long time was I was an aerospace engineer and I was always overqualified and underqualified at the same time. And there was never a place where I could get experience. But tech had plenty of room and I've gotten to sharpen my skills in that area. So your story is really, really impressive to me, and I really thank you for sharing that. I think there is a different breed. There's more science communicators now that have a really heavy science training background that I don't think we had a few, it feels like, and I could be wrong about this, but we've got Neil deGrasse Tyson, who's a big popular communicator. Obviously, we had Carl Sagan, and many others in between. And there's
Yeah,
a
you
lot of
can
folks
you can
online.
name them all on two fingers. It's
Yeah.
pretty good. At least you could up until I would say the mid 2000s.
Yes.
And I would say with the rise of the internet, of social media,
Hmm.
you're getting a lot more now, both
Yeah.
because the barrier to entry is lower
Mm.
and also because there's less of a stigma. Back when Carl Sagan
Oh.
was doing it, he was derided by many in the community as a popularizer, as though that was a negative. And I
Yeah.
still hear some of it. Myself, I'm 46 years old, so I've been doing this for a while, and I've heard from scientists that who am I? I'm just some blogger. I'm just some failed physicist
Mm.
who's doing communication because he couldn't make it as a as though my choices were no part of the equation at all. But that's what I am in their eyes. I'm a failed physicist. And to other successful journalists, I'm just some blogger. I'm
Mm.
just some scientist who thinks he can do this without the appropriate training. And I don't have a journalism degree. I don't have
Right.
the, you know, pros and cons, right?
Yep.
For me, my best analogy, and I've told this story to others before, but I'll tell it to you. Um, One of the things that resonated with me the most in terms of, hey, I'm a scientist, can I communicate? Um, was when I watched the movie Miracle. I don't know if
Mm.
you know about this, but they made a movie about the 1980 US men's hockey team.
Yes.
US men's hockey team in 1980 in a huge upset. This is a team of amateurs. This is way before like Michael Jordan's NBA Dream Team. This is
Mm.
back when you had amateurs playing in the Olympics, right? 1980 men's hockey team went up against the Soviet Union, full of, full grown Soviet men who'd been playing hockey their whole lives in the semifinals. And in a huge upset, the US team is down 3-2. They score a tying goal and they tie it at 3-3. And then with just a few minutes to go, they score a goal, a spectacular goal to take the lead 4-3. And as time is running out and the U.S. men's hockey team wins, announcer Al Michaels, very young Al Michaels, you probably know him from Monday Night Football, shouts, "Do you believe in miracles?" And then a few days later, they play Canada in the gold medal game and again come from behind and win. So these are the big hockey powerhouses, Soviet Union and Canada. US beats them both, wins the gold medal. 20 years later, they go to make a movie about it. They go to make a dramatization of it, and they have a struggle. Who are they going to cast to play the US men's hockey team?
Mm,
Are they going to cast the big name actors? Like the people who will bring in the big box
right.
office draw. Well, they can, but if they do that, they're going to have to teach these actors how to play convincing Olympic level hockey.
Right.
If you don't do that, you're going to wind up with a dud of a movie like, sorry, Russell Crowe, Cinderella Man, where you've
Hmm.
got a boxer who clearly cannot box his way out of a wet paper bag. And you're not going to want invest in a sports movie if you don't even believe the sports that are being played.
Right.
Or on the other hand, you can cast hockey players to go play these hockey players and teach them how to act. So I thought to myself, all right, well, maybe that's me. Maybe I'm the hockey player who needs to learn how to act rather than the actor who you're trying to teach to fake their way to playing convincing hockey. And maybe that's good. Maybe it's harder to have the expert knowledge of a theoretical astrophysicist than it is to write a complete sentence that you could communicate a thought to another person who isn't a theoretical astrophysicist. So, you know, you have skills and you have talents in life. The talents are the things you're born good at it, you're gifted at it, you cultivate it and you excel at it. Maybe I'm talented at math and science, and maybe I need to develop a skill
Mm,
when it comes to communication. But I can do that. You can develop a skill and be competent. No one is ever going to mistake me for Bill Shakespeare, right? No one's ever going to say, "Oh, that Ethan, he sure can write a sentence." But they are going to say, "Hey, he knows what he's talking about." When
yeah.
someone tells him something and it doesn't sound right, he's going to ask the right question that exposes if there's a flaw in their argument. And if I want something in its full context, he has a broad enough knowledge of this field that he knows how to put things in their proper context. And maybe that type of expert knowledge has a place in the journalism world.
Mm.
So, you know, sorry to derail that, but
No,
I
that was
did want
powerful,
to
man.
sort of
Thank you.
say that if, when people come at you and they naysay you and they tell you what you can't do, don't focus on your weaknesses. Focus on your
Right.
strengths. Focus on what you know you can do well. The things you can't do well, the things you are weak at, you can shore them up. I wasn't always as good of a science writer as I am now, but I started starts with a bang in January of 2008. That's almost 17 years ago. I've written in that time since between 3 and 6, I average 5 now, articles a week for almost 17 years.
That's
You
incredible.
do the math on that. How much have I written? I have written upwards of 5,000 articles since I started
Damn.
writing, an average of 2,000 words each. I've written 10 million words about science. Um, that's practice.
Yeah.
You want to be a good swimmer, jump in the pool. You want to be a good painter, pick up a brush. You want to be a good piano player, sit down and tickle those ivories. And you want to be a good writer, write. You will get good at it.
Let's go, Ethan. I love it. I love it. Now, I do want to be careful on time, so let's jump into Infinite Cosmos. Tell us about the book. What did it take to put this together? And if you don't mind, just a quick little snippet on what is JWST.
Yeah, this is a great question. Thank you. So Infinite Cosmos, right? This is my new National Geographic book, Visions from the James Webb Space Telescope. I was approached by National Geographic about this.
Mm.
I felt very fortunate. Someone who works at Space Telescope Science Institute, where they manage all the space telescopes,
Oh,
National Geographic had gone to them and said, "Hey, we wrote 3 books about the Hubble Space Telescope. Now we have the James Webb Space Telescope. We need to write a book about it. Who do you recommend?" Someone recommended me.
cool.
They came to me, and I was like, "Oh my God, of course." Like, you have no way of knowing this, but like, in 2020, I dressed up as the James Webb Space Telescope for
Amazing.
Halloween.
That's
I have
amazing.
I have the telescope mirror right here
Yeah.
on my wall. I made a 5-layer sun shield and walked around with
Oh,
it. It
that's
was
awesome.
glorious and ridiculous. But I have loved this telescope for more than a decade, since before it was launched.
Yeah.
Um, because to me, science is a series of receding frontiers. And if you want to know what's out there beyond the depths of what you've probed, you need a better tool and a better observatory. I like to say that the Hubble Space Telescope showed us what the universe looked like. The James Webb Space Telescope was designed to teach us how the universe grew up. What about the earliest stars and galaxies, the ones that Hubble can't see? What about galaxy clusters and how they form? What about the supermassive black holes at the centers of galaxies? Did they form from the stars that lived and died in those early galaxies that then gave rise to those supermassive black holes? Or did the supermassive black holes come first and then the galaxies formed around them? What about how stars are born? Is it just you get star formation and stars with stellar systems form and then all the gas is blown away? Or do you have a whole collection of failed objects, like things that would have been stars, except the gas got blown away by stars that formed earlier, and what else remains? And also, how do planets, especially Earth like planets, form in these young stellar systems?
Mm.
These were the types of questions that the James Webb Space Telescope was optimized to answer. So, a huge part of this book, the whole first chapter, doesn't focus on what did James Webb see, what did the JWST see. It focused on how was JWST constructed and why was it designed with the specifications that it was designed for. Then December 25th, 2021, right after all the testing, after all the going back and making sure all the fasteners are correct and all the components have been tested properly, everything's been stowed, it's been packed in the rocket, it's going to be launched. This was the critical moment. This happened during the pandemic on Christmas Day of 2021. I remember waking up at like 4 a.m. where I was to watch the live stream. How was it going to go down? Now, what was going on is they were planning on, okay, look, we're going to have a launch, and then JWST is going to have some onboard fuel. It's going to have to make some corrective burns so that it can wind up at its destination 1.5 million kilometers away from Earth in this stable orbit around the L2 Lagrange point, which is the point where, as Earth orbits the sun, it's the gravitationally stable point that keeps the telescope in the same orientation relative to the Earth sun position. So that was the goal, is to get it there.
Mm.
They had said, look, the rocket that launched JWST, that type of rocket, it had over 80 consecutive perfect launches, and then it had a failure where it went in the wrong direction. It was off by several degrees. If that were to happen to the James Webb Space Telescope, it would be a total loss. It would never reach the L2 Lagrange point, even if it spent all of its fuel, and it would never observe anything.
Yeah.
So when that critical launch moment came, we were all holding our breath. They were hoping that with the fuel they had on board, with the launch, and then after launch deployment, calibration, all of that, they were hoping to get between 5.5 and 10 years of science operations out of it. What happened at launch was amazing. I don't know if you speak French. I don't speak French. I learned Spanish in school. Um, when they launched this from French Guiana, you kept hearing this word ring out over the loudspeaker. The word was nominal, which is the French word for nominal. And it meant that everything was right on course. Everything was as designed. And you kept hearing that word over and over, ring out, ring out. And then at the end, after the stage 2 rocket, you get the separation where you see this telescope glittering in the sunlight, all packaged up. It's like a little square floating away. And then you saw something that, if you didn't know what was supposed to happen, you may not have been shocked, but I was shocked. I was shocked in the best way.
Mm.
What was supposed to happen is after 5 minutes, after separation of 5 minutes, the solar panels were supposed to deploy. And if that was successful, it meant it was getting power. What happened is the telescope released, and like less than 30 seconds after it released, the solar panels came out.
Mm.
That is not a mistake. That is what happened when you are your telescope and you are already on the right trajectory to go to L2. When
Wow.
you have the automatic sensors say you're already headed where you need to go, the solar panels automatically
Wow.
deploy.
Wow.
That signal meant this was such a perfect launch that it's like it didn't need to expend hardly any of that fuel that they were planning on it's going to have
It's
to expend.
crazy.
So, in not 5.5 years, not 10 years, this means JWST has an expected science lifetime of somewhere around 22 years.
The
And so
delta
that
V
moment of
thing.
launch
Oh,
was an enormous
that's crazy.
victory and an enormous sigh of relief for everyone who was both working on this telescope and who had hopes for what this telescope was going to deliver for us.
Mm.
And that second chapter focuses on the launch, the deployment, and the calibration. And what's wonderful is I got my hands on early pre release calibration images. Those are all
Wow.
included in this
Oh,
book.
so cool.
And then finally, in that third chapter, and the third chapter, I was like, this chapter has to be a full half of the book because it has to be what I'm most excited about is the sights and the science. What did Webb see? What did we learn from it? What did it teach us about the universe? And the answers, everything was spectacular and a lot of it was revolutionary.
Mm.
You build something not because you know, oh, I'm going to build this and I'm going to find a record breaking galaxy. And we did. We've broken the cosmic distance record many times over. And you say, I'm going to find the earliest galaxy cluster. And we did. You say, no, I want to build this to answer these big questions. I want to know, do supermassive black holes come from stars, or did supermassive black holes come first and then more stars and galaxies formed around them? We know it's that second one now, thanks to the combination of the James Webb Space Telescope and the Chandra X ray Observatory. You can ask, well, what happens when stars form? And JWST looked into the Orion Nebula and it found, hey, guess what? With my infrared eyes, I can find that there are a whole bunch of these Jupiter and super Jupiter mass planets that never formed stars, that never had a parent star, that when stars form, these are some relics that get left behind. And in fact, it found that a surprising 9% of them are actually multiple Jupiters in a binary system with no parent star. We did not expect that. But to me, the biggest surprise, the reason why when I talk about any new observatory that you build, you want to focus on your discovery potential.
Mm.
How much better are you at seeing in a set of wavelengths of light than every observatory that came before you? How much better are you in terms of resolution, in terms of light gathering power? Is James Webb Space Telescope took a look at the Fomalhaut system. This is the closest star to Earth that still has a debris disk, a planet forming disk around it. And so we took a look at it with JWST. Now, here in our solar system, we have the inner planets, we have an asteroid belt, we have some more planets,
Mm.
then we have a Kuiper belt. And out way beyond that, we have an Oort cloud.
Mm.
And we thought, for many good reasons, that this would be the template for how stellar and planetary
Right.
systems would form, that they would have like an inner belt, planets inside, more planets outside, a Kuiper-like belt, and then, some tiny stuff out there.
Mm.
When we looked at the Fomalhaut system, what did we find with JWST? We found an inner disk, which corresponds to the inner planets in the asteroid belt. We found a big outer belt that had already been seen with Hubble and ALMA. So we knew there was a Kuiper-like belt. Shocker. We found a third belt. We found an intermediate belt. We did not expect that. So, like I said earlier, sometimes you think you know what questions to ask, then you make a discovery, and now you have a new set of questions to ask. What's typical? Is our solar system with an asteroid belt and Kuiper belt 2 belts typical?
Mm.
Is Fomalhaut typical with 3 belts? Are there systems that have different numbers, 1 or 0 belts,
Yeah.
4 or more belts? Will Fomalhaut's intermediate belt survive long
Mm.
term, or will something destroy that? These are not questions we knew we needed to ask
Yeah. Yeah.
before the James Webb Space Telescope. Now, not only do we know we need to ask them, we don't know what the answers are. We went from assuming that we were typical to questioning, are we even common? Are
Mm.
we a rarity, possibly? Um, it will take more observations to find out, but now at least we know we're asking the right questions.
Absolutely. And I do want to close up here because I want to be respectful of the time. Folks, please go check out Infinite Cosmos. The book itself is such a piece of beauty. The what James Webb Space Telescope has brought back to us as far as data and visual depictions of the universe. Never mind the data that helps us understand it better. But the book is incredible. Go check it out. Where can they find it, Ethan?
You can buy this direct from Disney. National Geographic is owned by Disney. You can buy it at Disney. You can buy it at Amazon. You can buy it at Barnes and Nobles. You can buy it at Powell's City of Books, and you can get it wherever books are sold. There's both a hardcover version, which I highly, highly recommend,
It's
but you
nice.
can also get an ebook if you are an avid e-reader. Um, I I've looked at them both, and I'm a dead tree version kind of guy. I'm old fashioned like that. You could see I've got a big stack of books.
Nice.
Love them, but yeah, I say get it wherever books are sold, and if you're lucky enough to have me come through your neighborhood, I'll happily sign it to anyone.
Heck yeah, that's awesome. The one thing that really blew me away, having been born the year that shuttle, I mean that Hubble was put into orbit, and now with James Webb being old enough to understand the insanity of the 20-year saga that got the telescope to space, and then how much it's giving us back as far as data and content on a daily basis is is actually hard to keep up with, which is very impressive. And I think it's a testament to, like you were saying, the discoverability. What was the term you used for
The
how to
word I
design?
used was discovery potential.
Discovery potential. I love that. Um, I mean, it's blown away, I think, everyone's expectations who wasn't fully involved in the project. It had a literal perfect launch. All the bonus Delta V that's built into a mission just became a bonus, which is incredible. Is there anything, just as like a last closing sentence about James Webb or about cosmology and just the universe that you'd like to leave us with? Because it's been a great conversation so far.
If I could leave you with one more thing, I would like to emphasize that the James Webb Space Telescope should not be the end
Mm.
of astrophysics flagship missions. You have to say, look, this is how far we can go looking in these wavelengths of light with the James Webb Space Telescope. And it's incredible. It's like a factor of 100 or even 1,000 greater than previous observatories we built in that wavelength range. But we have a huge range of wavelengths to explore about the universe. We have no X-ray observatory that's better than the Chandra X-ray observatory, which is 25 years old now. We
Wow.
have never had a far infrared observatory since
Mm.
ESA's Herschel mission, the only far infrared observatory mission of the 21st century, and that's been defunct for more than a decade. And as far as optical goes, the Hubble Space Telescope is still the gold standard. 1990 technology is still the gold standard.
Mm.
Those three wavelength ranges, X ray, far infrared, and the optical, that's where if we said, I want to build the best space telescope I can build today, we have so much untapped discovery potential. I would love to see in my lifetime a new fleet of NASA great observatories that could reveal the universe to us like never before, because there is a whole universe out there to explore, and it belongs to you just as much as anyone else.
That's incredible, Ethan. Ethan, thank you so much for coming on Today in Space podcast and sharing about Infinite Cosmos and about yourself too. I think you shared some great advice today and some experiences that is everything that we wanted out of this People of Science segment. So thank you so much for coming on.
It was absolutely a pleasure. Thank you for having me. And thank you to all of you out there for listening to the two of us talk for the last hour.
If you're as jazzed up as I am, please go check out Infinite Cosmos Visions from James Webb Space Telescope. And spread love, spread science, and we'll see you on the next episode of Today in Space. See ya.